Welcome back. In this lecture I shall explain the selection of principal dimensions of reciprocating compressors with the help of a worked out example. Then I will discuss practical issues such as the capacity control of a reciprocating compressor and the different lubrication methods and selection of lubricants. So the specific objectives of this particular lesson are to discuss the selection of principal dimensions of compressor with a worked out example, then to discuss various methods of controlling capacity of reciprocating compressors and discuss compressor lubrication. At the end of this lesson you should be able to estimate principal dimensions of reciprocating compressors, explain the need for capacity control, describe various methods used for capacity control, and discuss the methods of compressor lubrication and important properties of refrigerant lubricating oils. Now let us look at a problem. The problem statement is like this: a reciprocating compressor is to be designed for a domestic refrigerator of 100 watt cooling capacity operating at an evaporator temperature of minus 23.3 degrees centigrade and a condensing temperature of 54.4 degrees centigrade. The refrigeration effect at these conditions is 87.4 kilojoule per kg. At the suction flange, the temperature of the refrigerant is 32 degrees centigrade and specific volume is 0.15463 meter cube per kg. Due to heat transfer within the compressor, the temperature of the refrigerant increases by 15 degrees. The indicated volumetric efficiency of the compressor is 0.85 and the leakage loss factor is 0.04 and the rotational speed of the compressor is 2900 rpm. So this is the problem. Okay, so let me just summarize the given input data. It is given that the cooling capacity is 100 watts, that means 0.1 kilowatt. Evaporator temperature is minus 23.3 degrees centigrade. Refrigeration effect is 87.4 kilojoule per kg. Temperature at suction flange is equal to 32 degrees centigrade. And specific volume of vapor at flange is 0.15463 meter cube per kg. And temperature rise in compressor is 15 degrees centigrade and indicated volumetric efficiency is 0.85. Leakage losses factor is 0.04 and the mean effective pressure MEP is equal to 5.224 bar, and finally the rotational speed of compressor is 2900 rpm. So this is the given information, and what is that we have to find? We have to find first the diameter and stroke of the compressor in centimeters, then the COP of the system if the actual mean effective pressure of the compressor is 5.224 bar. So let us solve this problem from the given input data. First of all, let us find out the mass flow rate of refrigerant. As you know, the mass flow rate of refrigerant is given by refrigeration capacity divided by the refrigeration effect. So in the problem it is mentioned that the refrigeration capacity is 0.1 kilowatt and the refrigeration effect is 87.4 kilojoule per kg. So if you substitute these values, we find that the required mass flow rate of refrigerant is 1.1442 into 10 to the power of minus 3 kg per second. Then let us find out the volumetric flow rate at suction flange. And the formula for volumetric flow rate is it's a product of mass flow rate of refrigerant into specific volume at suction flange. And just now we have found that the mass flow rate is equal to 1.1442 into 10 to the power of minus 3 kg per second, and the specific volume is given in the input data as 0.15463 meter cube per kg. So if you substitute these values, you find that the required mass flow rate of refrigerant at suction flange is equal to 1.7693 into 10 to the power of minus 4 meter cube per second. Then we have to find out the required compressor displacement rate. And as you know, the compressor displacement rate is nothing but the volumetric flow rate of the refrigerant divided by the actual volumetric efficiency. We know the volumetric flow rate, we have to find out what is the actual volumetric efficiency. So let us find out the actual volumetric efficiency. So in the last class I have mentioned that the actual volumetric efficiency of a reciprocating compressor, taking into account the heating in the cylinder and leakage loss factor, is given by this formula, where NV actual is the actual volumetric efficiency and eta V subscript TH is the indicated volumetric efficiency, which is given as 0.85. This we have to multiply by temperature of the refrigerant at suction flange, that is given, that is TS, that is given as 32 degrees centigrade, divided by the temperature of the compressor at the inlet to the temperature of the refrigerant at the inlet to the compressor, and it is mentioned in the problem that the refrigerant gets heated up by 15 degrees as it passes through the compressor. That means the temperature at the inlet to the compressor is 47 degrees, and the Ts and Tsc should be in the units of Kelvin. Okay, so we are converting this into Kelvin. Minus zeta L. Zeta L, as you know, is the leakage factor, and it is given as 0.04. So if you substitute these values, you find that the actual volumetric efficiency is given as 0.77. Now we know that from this we can find out what is the required swept volume of the compressor. This is nothing but the volumetric flow rate of the refrigerant divided by the actual volumetric efficiency. So if we substitute these values, we find that the required required swept volume of the compressor is 2.298 into 10 to the power of minus 4 meter cube per second. And we also know that the compressor displacement rate is equal to this formula, where I will explain. This small n is the number of cylinders, d is the diameter of the cylinder, L is the stroke length, and capital N is the RPM. So what we do is we write D and L, we club this into what is known as the stroke to bore ratio, that is theta. Okay, that means theta is equal to L by D. So if you are eliminating L, then this formula becomes pi d cube theta by 4 into small n into n by 60. Here all that we know is, we know the capital N because it's mentioned that it is 2900 RPM, and we have also found what is the required displacement rate. So there are three unknowns in this equation. One is the number of cylinders, and second one is the diameter of the cylinder, and the third one is the stroke to bore ratio. So we have only one equation and we have three unknowns. So what we have to do is we have to at least fix two parameters so that we can find out the unknown parameter from this equation. So what is normally done is, normally the number of cylinders, that is small n, and the stroke to bore ratio are fixed. Okay, once you fix these two, then only unknown is the diameter of the cylinder, so which we can find out from this equation. Okay. So as I have already explained, in the above formula, theta is equal to L by D, that is stroke to bore ratio, and small n is the number of cylinders, capital N is the rotational speed, and D is the bore of the compressor. And out of these we have to fix theta and N. So how do we fix these things? First let us look at the number of cylinders. Since this is a small compressor, we can select small n as 1, that means we have a single cylinder compressor. Okay, that is what is mentioned here. Number of cylinders we have chosen as 1, so n is 1. Then we have to fix the stroke to bore ratio. Stroke to bore ratio is theta, and at the here we have selected this as 0.8. What is the basis for selecting this as 0.8, and what is the effect of the stroke to bore ratio on the performance of the compressor? Let us look at this. Okay, so selection of stroke to bore ratio. The stroke to bore ratio theta is selected depending upon the delivery pressure as well as the speed of the compressor. So how does the delivery pressure affect the stroke to bore ratio, and how does the speed of the compressor affect the stroke to bore ratio? Let us look at it. What happens when theta is large? Theta, as you know, is L by D. Theta is large means the diameter is small. So when the diameter is small, you find that the frictional forces become large, because the frictional forces are proportional to the surface area to volume ratio. The surface area of a cylinder is pi d L and volume is pi d square by 4 into L. That means the frictional forces are proportional to 4 by D. So as you reduce D, the frictional forces increase. That means when you select large theta, that means small d, then there will be large frictional forces, and frictional forces really become very important when the speed is very high. Okay, so when the speed is high, we would like to minimize the frictional forces. That means for high speed compressors, we would like to have as large a diameter as possible. That means we have to select a smaller value of theta. Okay, then let us look at the other side. That means what happens when theta is small. When theta is small means the diameter is large. What happens when the diameter is large? When the diameter becomes large, the force acting on the piston becomes large. What is the force acting on the piston? What is the maximum force acting on the piston? The maximum force acting on the piston is nothing but the maximum pressure developed inside the compressor into the surface area of the piston. The surface area of the piston, as we know, is pi d square by 4, and the maximum pressure developed in the compressor is equal to approximately equal to the condenser pressure. That means the force acting on the piston ultimately becomes Pc into pi d square by 4. So when the condensing pressure is very large and when you also select a large d, you find that the force acting on the piston becomes very large. That means you have to design a very strong piston connecting rod and all that. That means the mechanical strength requirement and all increases as the diameter increases. That means in fact square of the diameter. Okay, and this factor becomes very important when Pc is high. So these are the two limits. That means small theta means higher frictional losses and large theta means higher mechanical strength requirement. Okay, so as a result, we normally find that a small value of stroke to bore ratio, that means large D, is selected when the speed is high, so that we can reduce the frictional losses. Okay, and on the other hand, when large values of stroke to bore ratio, that means small diameter is selected when high discharge pressure applications are encountered. Okay, that means for high discharge pressure application you have to go for small diameter, and for high speed application you have to go for large diameter. So some of the recommended values are like this. For vacuum pumps and high speed air compressors, normally theta value is about 0.5. As I have already mentioned, when speed is high, diameter should be large, that means theta value should be small. So theta value is around 0.5. And for fluorocarbon refrigerants, the industrial practice is to select a stroke to bore ratio of about 0.8. And for ammonia compressor, normally theta is selected as about 1. For ammonia compressor, normally the discharge pressures could be high, so you have to go for slightly smaller diameter. That is the reason why we have selected slightly higher theta compared to fluorocarbon refrigerants. And finally, for high pressure compressors, for example such as carbon dioxide compressors and all, we have to go for a high value of theta, that is about 4 to 6, so that the mechanical strength requirement will be small. So this is the criteria based on which you have to select the stroke to bore ratio. Okay, and in this particular example, I have not mentioned what is the refrigerant, but from common sense we know that in most of the domestic refrigerators we use either fluorocarbon refrigerants or hydrocarbon refrigerants. Nowadays we use hydrocarbon refrigerants. So for these things, typically the operating pressures are not so high. That means the condensing pressure is not so high. So generally, as I said, you have to select a theta of about 0.8. Okay, so this is the reason why we have selected a theta of 0.8 in this example. And nowadays the modern trend is to use high speed compressors. What is the advantage of using high speed compressors? From the expression for swept volume rate, that means the displacement rate of the compressor, we know that the swept volume is directly proportional to speed of the compressor. So when you increase the speed of the compressor, required swept volume becomes small. It has many benefits. Once the required swept volume becomes small, the compressor becomes very compact. That means the size of the compressor becomes small and its weight also becomes small, and its cost also becomes small. So there are a host of advantages when you go for high speed compressors. That is the reason why the latest trend, the modern trend, is to go for as high a speed as possible. Okay, so when there is one problem when you go for very high speed compressors, when the speed is very high. What is the problem? When the speed is very high, the heat generation also will be high, okay, and there won't be sufficient time for heat to be rejected from the compressor. Okay, so this is one constraint on the highest speed of the compressor. Okay, that is what is mentioned here. And as I have already mentioned, when you have high speed compressors, normally we go for larger diameter so that we can reduce the frictional losses. And here actually not only the rotational speed, the piston speed is also important. Of course, the piston speed and rotational speed are related by this expression. Piston speed is nothing but n into stroke length by 30. This n is the revolutions per minute, and the 30 comes here because in one revolution it travels 2 stroke lengths. It completes in one revolution, it completes a distance of 2 stroke length. That is the reason why we have 30 here. And normally the recommended piston speed is about 2 to 5 meters per second. In fact, it is very surprising to note that over the last many decades, this recommended piston speed has not really changed. That means the range always lies between 2 to 5 meters per second. There are many practical reasons why it is like this. And normally smaller piston speeds are used in smaller compressors, and larger piston speeds are used in larger compressors. Okay, so from this discussion, the stroke to bore ratio theta is selected as 0.8. Once you have selected theta and n, then all that you have to do is substitute the value of theta and n and the displacement rate in the equation shown before. Then the only unknown is the diameter. So from this example, you find that the diameter of cylinder is 1.963 centimeter, and the stroke length L is nothing but theta into d. Theta is 0.8, 0.8 into d is 1.5704 centimeter. This is how normally the principal dimensions of a compressor are chosen. Of course, there are a lot of issues which have to be considered. For example, just now I mentioned the selection of the number of cylinders. Since this is a small refrigerator, we selected n as small n as 1, that means a single cylinder compressor. When the capacity becomes large, one has to go for more number of cylinders, okay, and normally you can go as high as 16 cylinders. So again, everything depends upon the given problem. Okay, and the speed here is mentioned as 2900 rpm. There is a reason behind this. Normally in small domestic refrigerators we use two-phase induction motors. So if you assume a frequency of 50 hertz, then the maximum speed is 3000 rpm, and if you take care of the slip, then the speed will be about 2900 to 2950 rpm. That's the reason why the speed is given as 2900 rpm. Okay, so you have to decide certain parameters, and then you have to use the given input data, and finally you have to arrive at the stroke and bore of the compressor. Okay, then second part of the problem is to find out the COP of the system. We know that, in fact, if you remember in the last class, I have mentioned that the concept of mean effective pressure, actual mean effective pressure, is very useful because it is defined in such a way that when you multiply this actual mean effective pressure into the displacement rate of the compressor, that will give you the actual power requirement of the compressor. Okay, so if you can find out what is the mean effective pressure, all that you need to know is the displacement rate of the compressor. Okay, so here we have its input is given that the mean effective pressure is 5.224 bar, and the displacement rate we have found to be 2.298 into 10 to the power of minus 4 meter cube per second. So if you substitute these values, you find that the actual power input is given by 0.12 kilowatt. So if you substitute this in the expression for COP, COP is nothing but the refrigeration capacity divided by the power input to the refrigerator, then that you will find that it's 0.1 divided by 0.12, that means the COP is 0.833. Okay, this is a practical problem, and very simple problem. All that you have to do is you have to use the right equations and you have to use the right data. Okay. Now let us look at some of the practical aspects of reciprocating compressors. First one is the capacity control of reciprocating compressors. Why do we need capacity control? Normally when you design a refrigeration system, you always design it in such a way that it operates satisfactorily even when the load is maximum. That means you normally design it for peak load conditions. And when do these peak load conditions occur? The peak load conditions occur when the cooling load is maximum or when the condensing temperature is very high. Okay, so normally we select the components of the refrigerant system including compressor to meet the peak load requirements. Okay, so that's how the compressor is selected. But you find that most of the time the load may not be at its peak. That means either the cooling load is less than the peak or the condensing temperature is lower. Okay, that means under these circumstances the cooling load requirement will be less than the design load or peak load. So what happens, since you have selected the compressor to suit the peak load requirements and the system is operating at less than the peak load, then the compressor becomes oversized. Okay, at off design conditions. Okay, so when the compressor becomes oversized at off design conditions, what happens? What exactly is the main function of the compressor? The compressor has to take out the refrigerant vapor at the rate at which it is generated in the evaporator. That means the mass flow rate through the compressor should be equal to the mass flow rate of the refrigerant in the evaporator. That means the rate at which vapor is being generated in the evaporator should be equal to the compressor mass flow rate. Then the evaporator temperature will be at the design value. Under off-load conditions, that means under load conditions which are lower than the design load, the compressor becomes oversized. That means compressor will be trying to take more refrigerant vapor than is generated in the evaporator. Okay, so that means less vapor is generated because the load is less, but the compressor is taking out more vapor. So what happens? So there is an imbalance between the rest of the system and compressor. As a result, the system will finally arrive at a balanced condition, and this balanced condition will be at a lower evaporator temperature. That means ultimately at low load conditions, if you do not do any capacity control, then the evaporator temperature of the system will be low. Okay, and the system will attain a balance. Now when the evaporator temperature is low, there are many problems. First of all, if you are using it for, let us say, cold storage requirements, then since the evaporator is operating at low temperatures, the humidity of air also will be low. That means there will be dry conditions in the cold storage. This may lead to higher weight losses, moisture losses. Okay, and it may also lead, if the temperature is so low that it falls below 0 degree centigrade, then it may lead to frosting. On the other hand, if you are using not air but some liquid such as water as an external fluid, then there is a danger of the water freezing inside the pipelines because the evaporator temperature has fallen below 0 degree centigrade. Then as you know, when water freezes, its volume increases, the pipelines may burst. That means if you want to operate the system satisfactorily at less than the design load conditions, you must make sure that the evaporator temperature is not falling too much below the design value. Okay, this is only possible only when you regulate the capacity of the compressor. Okay, that means all practical systems have to have some means of regulating the capacity of the compressor. Normally when we say the capacity control, we generally mean reduction in capacity. Okay, because in general it is not possible to increase the capacity more over and above that of the design, because design load itself is the peak load. So whenever we say capacity control means capacity reduction. Okay, so capacity reduction is a must in any practical refrigeration system. So let us look at what are the different ways by which capacity control of reciprocating compressors is achieved. Okay, so let me summarize whatever I have explained now. Refrigerant compressors are normally designed for peak load conditions. Without capacity regulation, the evaporator temperature decreases during part load conditions, as I have already explained why it happens, and reduced evaporator temperatures lead to problems such as low air humidity in the refrigerated space, frosting of evaporator coils, and freezing of the external fluid. This obviously indicates a need for controlling the capacity of the compressor. So this is the need for capacity control. And what are the different methods available for capacity control of compressors? The first method is known as cycling or on-off control. The second method is back pressure regulation by throttling of suction gas. The third method is what is known as hot gas bypass. And the fourth method is known as unloading of cylinders in multi-cylinder compressors. And finally, you can also regulate the capacity by compressor speed control. Now let us look at each one of them, and let us look at what are the typical features, what are the advantages and disadvantages of these methods. First, let us look at cycling control or on-off control. So this type of control is normally used in small refrigerant systems such as domestic refrigerators, room air conditioners, and water coolers. I am sure that all of you must have noticed that domestic refrigerators or room air conditioners are cycling devices. That means once the required temperature is achieved inside the refrigerator, the compressor is simply switched off. Okay, and after some time the compressor again is switched on. That means there are periods during which the compressor is running, and there are periods during which the compressor doesn't run. This typically happens in small systems such as room air conditioners, water coolers, and domestic refrigerators. Okay. And how this is done? Normally this is done by using a thermostat which senses the temperature of the refrigerated space or evaporator temperature, and in turn controls the compressor on off. So normally again you must have noticed in domestic refrigerators and evaporators a thermostat is used, and using the thermostat you can really set the temperature inside the refrigerator space or inside the air conditioned space. Okay, and the function of this thermostat is to sense the temperature. What temperature depends upon the design of the system. For example, the temperature that is sensed by the thermostat could be the refrigerated space temperature itself, or it could even be the evaporator temperature. So depending upon where you have located the sensor, it will be sensing some temperature, and based on the values of that particular temperature, it will take the control action. And here the control action is either on or off. Okay, so it normally acts acts as a switch, and when the switch is closed, there will be power supply to the compressor and compressor runs, and when the switch is opened, there is no power supply to the compressor and compressor stops. Okay. And as I have already explained to you, when the refrigerator space or evaporator attains a cutout temperature, the thermostat switches off the compressors. When we talk about the controls, typically a thermostat, we introduce some new terms. One is what is known as a cutout temperature. Cutout temperature is the temperature at which the thermostat switch opens. That means power supply to the compressor is stopped. Okay, that means compressor becomes off. This temperature is known as cutout temperature. And again the compressor has to be switched on when the temperature rises to a cut-in value. Okay, so what happens when the compressor is switched off? When the compressor is switched off, there is no refrigeration effect inside the refrigerated space, and as you know, the refrigerated space is at a temperature that is lower than the surroundings. Since there is a temperature difference between the surroundings and the refrigerated space, there will be heat leak into the system. So the system temperature increases. When the system temperature goes beyond, system temperature or evaporator temperature goes beyond a set point, what is known as cut-in temperature, again the refrigerant system should be switched on. Okay, that means when the thermostat senses that the temperature has reached the cut-in temperature, then again it supplies, the switch is closed and the compressor starts running again. Okay, so in a nutshell, when the temperature reaches cutout temperature, compressor is switched off, and when the temperature reaches a cut-in temperature, compressor is switched on again. Okay, so this is the principle of a thermostat control, on-off control. So what happens because of this? Because of this, you find that the temperature in the refrigerated space or evaporator temperature varies between the cutout and cut-in values. Okay, so temperature does not remain constant. In fact, if you look at any air conditioned space or refrigerator, you always find that the temperature continuously fluctuates between the cutout and cut-in values. Okay. And the difference between cut-in and cutout temperature is known as differential of the thermostat. Okay, cut-in temperature is higher than the cutout temperature, and this difference is known as differential. And the differential of the thermostat can be varied by an internal adjustment. Let me give an example. You can have a thermostat which has a cut-in temperature of let us say 10 degrees centigrade and a cutout temperature of 9 degrees centigrade. That means when the thermostat senses that the temperature is 9 degrees centigrade, the switch opens and the compressor is switched off, okay, at 9 degrees centigrade, which happens to be the cutout temperature. And as a result of compressor being switched off, the refrigerated space temperature or evaporator temperature increases, and when this temperature reaches 10 degrees centigrade, then the system is switched on again. Okay, that means the temperature variation is between 9 to 10 degrees centigrade, and the difference between these two, that means 10 minus 9 is equal to 1 degree centigrade. This 1 degree centigrade is known as the differential of the thermostat, and you can change this the differential of the thermostat, and this adjustment is generally done internally. Normally this is factory set, but if you want to change it, you have to open the thermostat, and inside the thermostat there will be a mechanism for varying the differential. For example, you can vary the differential. You can keep the cut-in temperature as 9 degrees centigrade, and you can 10 degrees centigrade, and you can change the cutout temperature to, let us say, 8 degrees centigrade. Okay, so instead of operating at 10 degrees and 9 degrees, it can operate between 10 and 8 degrees. That means you have increased the differential from 1 degree to 2 degrees centigrade. This adjustment is possible. Okay, so this is differential. And the level of temperature at which the thermostat operates is called as the range of the thermostat. So you have the difference between cutout and cut-in temperature, and you also have the absolute values of these temperatures. For example, in the example I have discussed just now, 9 degrees and 10 degrees are the levels at which the thermostat switch is operating. So this is known as range. Okay, 9 and 10 degrees, right? And the range of the thermostat can be varied by the customer by turning the thermostat knob. So you can vary the, as a customer you can change the range. That means if you want a colder settings, then what you can do is you can push the operating temperatures to lower temperature by turning the thermostat towards colder side. So this you might have seen in your domestic refrigerators. When you turn the thermostat knob to colder side, instead of operating between 9 and 10 degrees, it may operate between 5 and 6 degrees. Okay, so this is in the hands of the customer. Similarly, air conditioned space, you can make the room warmer or colder by controlling the thermostat knob. So when you are actually rotating the knob of a thermostat, what you are doing is you are actually varying the range of the thermostat. Okay. Of course, in some of the systems, instead of using a thermostat, you can use what is known as a pressostat. Okay, that means instead of sensing the temperature of a conditioned space or temperature of the evaporator and taking a control action, you can also sense the pressure of the evaporator. Okay, instead of sensing the evaporator temperature, you can sense the evaporator pressure. When the evaporator pressure falls below a certain cutout pressure, then you can switch off the compressor, and when the evaporator pressure increases to the cut-in pressure, then you can again switch on the compressor. Okay, that means instead of operating between cutout and cut-in temperatures, it will be operating between cutout and cut-in pressures. Okay, and the device which is used for achieving this purpose is known as a pressostat, not thermostat. Okay, this type of, as I said, this type of device is called a pressostat, and it is designed to take control action by sensing the evaporator pressure. Now, this is a principle of on-off control, and where do we use on-off control, and what are the advantages and disadvantages of this control? The on-off control, as you might have seen, is satisfactory in applications where the fluctuation in product temperature due to on-off control is acceptable. So, whenever you are using cycling control or on-off control, there will be definitely a temperature fluctuation inside the refrigerated space. Okay, if this temperature fluctuation is acceptable and nothing, no harm takes place, even if the temperature varies, then you can use this on-off control. Okay, typically in room air conditioners or in domestic refrigerators, a temperature variation of 1 or 2 degrees doesn't make much difference. It doesn't really spoil the products, or it doesn't really lead to a great deal of discomfort. Okay, so we can afford to use this kind of a control in these applications where the temperature is not very important. Okay, it's important but not so important. So thus it is suitable when the and it is also suitable when the thermal capacity of the product or the refrigerated space is large, so that small variation in it can give sufficient variation in evaporator temperature. Even though just now I mentioned that the refrigerated space temperature in these applications is not very important, that doesn't mean that it can vary over a large range, because otherwise the product will get spoiled. Okay, so the variation should be small, right, but there should be some variation, and this variation should be tolerable. Normally, if you want to reduce the variation in the product, because you are ultimately concerned about the product or the people, you are not really interested in the temperature of the evaporator. Okay, and if you are sensing the evaporator temperature, okay, so if you have a system where the thermal capacity of the product is very large, okay, then a small temperature variation in the refrigerated space can lead to a large temperature variation in the evaporator. Okay, that means you can have a large difference between cutout and cut-in values of the evaporator temperature. At the same time, the refrigerated space temperature doesn't vary much because of its high thermal capacity. So these are the applications under which this on-off control is good. Okay, otherwise it's not good. Okay. So on-off control is not good when the temperature has to be regulated within a small range, in which case the compressor has to start and stop very frequently. Okay, what happens? It is not that it doesn't work. You can have a difference of 0.1 degree between cutout and cut-in. That means you can have a cutout temperature of 9 degrees and a cut-in temperature of 9.1 degrees. Okay, as far as thermostat is concerned, you can design such thermostats. But what happens? So if you have only a 0.1 degree differential, that means the compressor starts and stops very frequently. Okay, this has many practical problems. Normally, when the system is very large, it cannot start and stop so frequently. Okay, whereas small capacity systems can stop and start more frequently. Okay. So as I have already mentioned, small compressor motors can be cycled for about 10 cycles per hour, whereas large compressor motors are normally not allowed to start and stop for more than 1 or 2 times in an hour. Okay, so this puts a restriction on the minimum value of differential. That means you have to have a certain minimum value of differential so that the number of on and off can be controlled and can be within the practical limits. Okay, so this is a constraint on using the thermostat for on-off control. So, though on-off control introduces cycling losses, it may be better than operating the system at part load with poor COP. Okay. So, what happens during on and off? For example, if you look at a domestic refrigerator, where we typically use a capillary tube as an expansion device. So, when you are switching off the system, there will be a pressure equalization. That means the entire system pressure will reach an equilibrium value. That this happens as the high pressure refrigerant vapor or high pressure refrigerant liquid from the condenser flows through the capillary tube and it enters into the evaporator, so that the pressure difference vanishes. That means ultimately there will be no pressure difference between the condenser and evaporator. So, what is happening during this process? During this process, you are introducing hot refrigerant into the evaporator. That means into the refrigerated space. That means you are adding heat to the refrigerated space, which has got to be taken out again, right. So, this kind of a loss is known as a cycling loss. So, whenever you have on-off type of control, and whenever you are using devices such as capillary tube for throttling, then you have cycling losses. Okay. So, this is one of the disadvantages of on-off control, but in many applications this may be tolerable rather than operating the system at part load condition. That means you operate the system continuously at a part load condition, and at part load condition you are getting poor COP. Okay. That means the efficiency will be low. So, the low efficiency under part load conditions may be much higher than the cycling losses. Okay. So, under such circumstances thermostat control is good. And since on-off control is inexpensive and simple, it is widely used in small capacity systems, as I have already mentioned. Okay. This is the most widely used control in almost all small capacity refrigerant systems, because it is inexpensive. In small capacity systems, cost is a major factor, and it is also very simple. Okay. So, now let us look at the second method of capacity control. This is capacity control by back pressure regulation by throttling of suction gas. This method is effective in reducing the compressor capacity. Okay, what do we do? As the name implies, what do we do? How do we reduce the capacity of the compressor? Using this method. In this method, what we do is we introduce a valve between the evaporator outlet and the compressor inlet. Okay, in fact, I have explained this in the last class when we were discussing compressor capacity during the peak pull down. Okay. So, what is the purpose of this valve? Whenever you want to reduce the capacity of the system, you close the valve. That means you are throttling the refrigerant across this valve. When you throttle the refrigerant, what happens is the pressure drops. That means the pressure of refrigerant at the inlet to the compressor will be lower than the evaporator pressure because of the throttling process. Once you reduce the suction pressure, as you know very well, the volumetric efficiency of the compressor reduces and the capacity of the compressor reduces. Okay, so this is the principle behind capacity control using back pressure regulation. Okay. However, this method, even though I have mentioned here, is not normally used for regular capacity control, as it does not reduce the compressor power input proportionately. Consequently, it is energy inefficient. Okay. So, this method, as I have already mentioned, is effective in controlling the capacity. You can control the capacity by using a throttle valve, but the disadvantage is you are getting less refrigeration capacity, but at the same time you are not able to reduce the power input to the compressor. Okay, the throttle valve does not reduce the power input to the compressor in the same proportion. As a result, the COP at part load conditions will be less than the COP at design conditions. Okay, that means this method is not energy efficient. Okay, so that's the reason why normally this back pressure regulation for capacity control is not used in practice. But this method is generally used, as I have already explained in the previous classes, for reducing the peak power requirement during the pull down. Okay, so this method is normally used during the pull down period so as to avoid the power peak, as explained in the earlier lectures. Now let us look at the third method, which is quite popular. This method is known as hot gas bypass method. Let me explain what is the hot gas bypass method here. As you can see here, you have the four basic components: evaporator, compressor, condenser and the expansion device. In addition to this, you have a hot gas bypass. Okay. So, normally when the system is operating at design load, this valve will be closed. Okay. When this valve is closed, the refrigerant from the compressor flows to the condenser and it meets the design load requirements. But when the load falls, this valve opens. Okay. This is hot gas bypass valve, opens at low load conditions. Okay. When this valve opens, what happens? As you can see, some of the refrigerant, instead of going to the condenser and expansion device and evaporator, is bypassed and it comes back to the compressor inlet itself. That means it will be cycling at this point itself. Okay, it does not go through the rest of the circuit. As a result, the refrigerant flow rate through the compressor remains constant, but the refrigerant flow rate to the evaporator is reduced. As a result, the evaporator capacity reduces, so which matches the less load. Okay, so this is the principle of hot gas bypass. Normally, this valve is controlled by sensing the pressure here. That means you will be sensing the pressure at the evaporator, and that is connected to this valve. When this pressure falls below the design pressure, that means the load is less and this valve opens, and once this valve opens, then there will be bypass, and the refrigeration capacity also reduces to meet the load. Okay, so this is one method of hot gas bypass. You can also have another hot gas bypass method, where instead of sending this hot gas to the inlet to the compressor, you can send it to the inlet to the evaporator. That means you are not doing this, but you are using this, okay, this valve. So this valve is again controlled by the pressure of the evaporator, and when the evaporator pressure falls, this valve opens. When this valve opens, what is happening? The refrigerant vapor comes directly to the inlet to the evaporator. Okay, it is not going to the inlet to the compressor. So it flows through the evaporator. Okay, and as it flows through the evaporator, since it is in a vapor form, it does not contribute to the refrigeration effect, so refrigeration capacity reduces. Okay, so that means you can have hot gas bypass either to the inlet to the compressor or to the inlet of the evaporator. Okay, both the methods are possible. Okay, so now let us look at the characteristics of hot gas bypass method. Hot gas bypass to suction side is an effective method of controlling the capacity. When the evaporator pressure falls below a predetermined value, a hot gas bypass valve is opened and hot refrigerant from the discharge side flows back into the suction side of the compressor, as I have already explained. And a constant pressure expansion valve can be used as a hot gas bypass valve. And what are the, as I said, this is an effective method for controlling the capacity, but obviously this method has certain disadvantages. What are the disadvantages of this method? First disadvantage is there is little or no reduction in compressor power consumption at reduced loads. This is one important thing which you have to keep in mind. That means what is the performance of the system at part load conditions. Okay, ideally we would like to maintain the same COP under all load conditions. Okay, whatever is the COP at design condition should also be the COP at part load conditions. But in general, most of the cases we find that the part load COP is always less than the COP at design load conditions. Okay, but this reduction should be minimized. Okay, and when you are using a hot gas bypass method, you find that refrigerant capacity is reducing, but the power input is not reducing proportionately. As a result, the COP at part load conditions will be lower than the COP at design conditions. Why does it happen? Why power input does not reduce? Power input does not reduce because when you are doing hot gas bypass, for example, when you are sending the hot gas to the inlet of the compressor, then the suction gas becomes superheated. Okay, that means you are pushing the compression process away from the saturated vapor region. When, as you know, when you push the compression process away from the saturated this thing, the isentropes are flatter in that range. So for the same pressure rise, you find that the work of compression will be higher. Okay, so as a result the COP reduces. Okay, so this is one of the disadvantages of this method. And another major disadvantage is excessive superheating of the suction gas, resulting in overheating of the compressors. Okay, so just now I have explained that when you are sending the hot gas to the inlet of the compressor, the suction gas becomes hot. That means it gets superheated. And once it becomes superheated, its ability to cool the compressor reduces, and this factor is very important in particularly hermetic type of compressors, where if you remember, the suction gas is used for cooling the compressor and the motor, but if the suction gas is entering at a high temperature, it cannot cool the motor and compressor effectively. Okay, so when you are using hot gas bypass, the compressor cooling gets affected, and if the superheat is very large, that means you are bypassing lot of hot refrigerant back to the compressor inlet, then the superheat will be very high. Once the superheat is very high, the compressor cooling will be very low. Okay, this will affect the compressor life and performance, right. So this is the second disadvantage of this method. Of course, overheating of the compressor can be reduced by sending the hot gas bypass to the evaporator inlet. So, you can minimize, you can reduce this superheating, as I have already explained, by sending the hot gas not to the inlet of the compressor, but to the inlet of the evaporator. Okay. By this method you can reduce the superheat. This method is also advantageous, that means sending the hot gas to the inlet of the compressor, because the refrigerant flow rate through the evaporator remains same. As a result, the velocity of refrigerant through the evaporator remains same, which will ensure the return of the oil to the compressor. Okay. That means sending the hot gas to the inlet of the evaporator is much better than sending it to the inlet of the compressor. Okay. Hot gas bypass is normally used for regulating the capacity of small systems. Okay, this is not really not normally used in large systems, but it is used in small systems. However, in conjunction with other efficient methods, hot gas bypass is used when it is required to regulate the capacity down to 0% or for unloaded starting. Okay. So, even though it is not used for capacity control in large systems, along with some other efficient capacity control method, hot gas bypass method can be used to fine tune the capacity control. That means you can using the hot gas bypass along with another efficient method, you can reduce the capacity of the system almost to 0%, okay, of the design load. So, this is one and you can also use hot gas bypass method to reduce the peak load requirements during the pull down. Okay. So, this is a general practice. Now, let us look at the fourth method, that is the unloading of cylinders in multi-cylinder compressors. As the name implies, this method is followed in multi-cylinder compressors, and unloading of cylinders is another effective method of regulating compressor capacity. And what is this method? In this method, the capacity control is achieved by keeping the suction valves of some of the cylinders open during the compression stroke. That means what we do is we keep the suction valves open throughout the cycle, okay, of some of the cylinders, not all the cylinders. So, when you have a multi-cylinder, let us say 16 cylinders, and you want to reduce the capacity. So, some of the cylinders, maybe 4 or 5 cylinders, you can keep the suction valve forcibly open even during the compression stroke. So, when you are keeping the suction valve open during the compression stroke, what happens? Whatever gas is entered into the cylinder during the suction will flow back into the evaporator during the compression stroke also, because during the compression stroke suction valve is open. So, as the pressure increases due to the pressure difference between the compressor and the evaporator, the gas flows back into the evaporator. Okay. So, this is the method followed in these systems. Okay. As a result, the suction vapor drawn into these cylinders during suction stroke is returned to the suction line during the compression stroke. This is done with the help of pressure sensing switch, which senses the low pressure in the evaporator and opens some of the suction valves. Okay, so you have to use a pressure sensing switch, which will be sensing the pressure, and once the pressure inside the evaporator is low, that means the load is low. So, it keeps some of the suction valves open. In addition to capacity regulation, this method is also used during pull down, so that the peak power point can be skipped. This method is efficient as the required power input reduced with reduced cooling load, though not in the same proportion. So, this is an efficient method compared to other methods. That means the loss in COP is not so high. That is the reason why this method is quite commonly used in large capacity systems where COP is very important. Okay, and when you are using this method, the power requirement will reduce, but not in the same proportion. Okay. Right. So, let us look at the final method, that is the compressor speed control. So, if you remember from the example, you have seen that the mass flow rate of refrigerant is proportional to the displacement rate, and which in turn is proportional to the speed of the compressor or RPM of the compressor. So, when you are reducing the speed of the compressor, you can reduce the displacement rate of the compressor. That means you can reduce the mass flow rate of refrigerant through the system. When you are reducing the mass flow rate, then you can obviously reduce the capacity. Okay. So, this is the principle behind capacity control using speed regulation. Okay. This is a very efficient method, because when you are reducing the speed, the power input also reduces almost proportionately. Okay. So, this is a good method. So, as I said, it is one of the most efficient methods, because the power input reduces almost in the same proportion. However, there are certain constraints. For complete control, we have to have a variable frequency drive. Okay, so if you want to control the speed of the compressor, you have to have a variable frequency drive. Of course, if you have open type system with belt drive or gate drive, then you can also reduce the speed using these things. But in general, a variable frequency drive is more commonly used in smaller systems. Okay, and once you have a variable frequency drive, it increases the cost of the system. In addition to reducing the speed too much, of course, this also has a drawback. For example, if you are reducing the speed of the compressor very much, that means the refrigerant flow rate is reduced considerably. Once the refrigerant flow rate is reduced considerably, the velocity of refrigerant through evaporator reduces because the cross section area is same. Once the velocity reduces very much, then the oil carrying capacity of the refrigerant will reduce, and this will also affect obviously the cooling capacity of, the cooling of the compressor. Okay, so this puts a lower limit on the minimum speed that you can use for capacity control. Okay. Now let us quickly look at compressor lubrication. Normally any compressor requires lubrication, and reciprocating compressors require lubrication to reduce wear between several rubbing parts. And normally lubricating oil is used to lubricate the compressors, like in my other systems, and the lubricating oil is usually comes in contact with the refrigerant and mixes with it. This is one typical problem in refrigerant compressors, because the refrigerant and the oil come in contact. So it is essential to select a suitable oil in refrigerant compressors. This is a very critical parameter, and the important properties that must be considered while selecting lubricating oil in refrigerant compressors are chemical stability, pore or flock points, dielectric strength, and viscosity. In addition, we also have to consider the nature of the refrigerant used, type and design of the compressor, evaporator and compressor discharge temperatures while selecting a suitable lubrication system. Now let me quickly explain the chemical stability. Why do we require chemical stability? We require chemical stability because the oil should not undergo any chemical changes for many years of operation, and this is especially critical in hermetic compressors, where you are not supposed to change the oil for many years, that means for 10 years or more. So it has to be chemically stable for almost 10 years. And another problem in hermetic compressors is that since the discharge temperature is normally high, the oil should be stable even under very high discharge temperatures. So the chemical stability of the oil is inversely proportional to the number of unsaturated hydrocarbons present in the oil. That means higher the number of unsaturated hydrocarbons, smaller is the chemical stability. So for refrigerant compressors, oil with low percentage of unsaturated hydrocarbons are desirable. And then next let us look at pore or flock points. The pore point of the oil is the lowest temperature at which the oil can flow or pour. And this fact is very important in systems working at low evaporator temperatures. What happens at low evaporator temperatures? If the oil has a high pour point, then when the temperature is low, it will stop flowing. That means it may become a solid or it may congeal. If this happens, then the system starts malfunctioning. Okay, and it is found that the pour point depends upon the wax content. That means higher the wax content, higher will be the pour point. And for low temperature applications, obviously we require oils with low wax content so that we can have low pour point. And flock point is important for oil soluble refrigerants, and it is defined as the temperature at which wax will start to precipitate from a mixture of 90% R12 and 10% oil by volume. This is the definition of flock point. And the flock point of the oil is a measure of the tendency of the oil to separate wax when mixed with an oil soluble refrigerant. So this is important only for these refrigerants. And since the tendency for wax to separate increases with amount of oil in refrigerant, the concentration of oil in refrigerant should normally be kept below 10%. Okay, you should not have too much of oil in the refrigerant. Now let us look at dielectric strength. As you know, dielectric strength of the oil is a measure of the resistance to the flow of electric current. And in refrigerant compressor, it is normally expressed in terms of the voltage required to cause an electric arc across a gap of 0.1 inch between two poles immersed in oil. So this is how it is measured in case of refrigerant compressor. That means you maintain a gap of 0.1 inch between two poles, and you immerse these poles in a oil and then measure the dielectric strength. A high dielectric strength is an indication of the purity of the oil. And this parameter is very important in case of hermetic compressors, as an oil with low dielectric strength may lead to shorting of the motor winding. So, we have to have refrigerants having refrigerant lubricating oils having high dielectric strength, so that the shorting of the winding does not take place. Okay. The final important property is viscosity, and as you know, viscosity is very important in any lubricating system, and the viscosity of the oil should be maintained within certain ranges. What happens when the viscosity is very low? When the viscosity is very low, the wear between the rubbing surfaces will increase, and this also will not seal the gaps properly. One of the primary objective of lubrication is to lubricate the rubbing components, but it also has secondary objectives like sealing the components, okay, so that the refrigerant leakage can be reduced, and it also has to act as a coolant in certain applications. Okay, so these are secondary objectives. So when the viscosity is very low, it will not act as a good sealant. That means the gaps will not be filled with the oil, so there could be leakages, right? And what happens when the viscosity is very high? When the viscosity is very high, the gaps may not be filled with the oil, because the oil may not flow into the gaps, especially when the gaps are very small. So this again will lead to excessive wear. And this problem is complicated in refrigerant compressors because the viscosity of the oil varies considerably with temperature and refrigerant concentration. So as I said, this problem is very complicated in refrigerant compressors, because in refrigerant compressors oil comes in contact with the refrigerant, and once the refrigerant mixes with the oil, its viscosity reduces. Also the temperature varies during its operation, and when the temperature increases, viscosity again reduces. That means the viscosity of the oil keeps varying. Okay, so this complicates the design of the lubricating system. And both mineral oils as well as synthetic oils have been used as lubricating oils in refrigeration. Mineral oils have to be refined to improve their chemical stability and reduce their pore or flock points. Okay, you cannot use the mineral oils in unrefined form, you have to refine them. And synthetic oils have been developed to suit the requirements of chemical stability, good lubricity, good refrigerant solubility, lower pore or flock points, and required viscosity. That means you can synthesize oils to suit your requirements. And let me mention the methods of lubrication. And the lubrication can be either splash type or force feed type. And normally small compressors are splash lubricated, and larger compressors are force feed type lubrication. Okay, and in the force feed method, lubrication we use an oil pump for circulating the lubricating oil. Okay, as the name implies, force feed means an oil pump is used, which will be pumping the lubricating oil through the various gaps in the rubbing components. And generally this is used in larger systems. And in splash type of lubrication, the compressor crankcase, which acts as an oil sump, is filled with oil to a certain level. As the crankshaft rotates, the connecting rod and crankshaft dip into the oil sump, causing the oil to be splashed on the rubbing surfaces. As the name implies, in splash type, as the crankshaft and connecting rod rotate, every time it rotates, it gets dipped into the oil sump, and it picks up some oil and it splashes the oil onto the rubbing components. Okay, so that's why you call it as splash type of lubrication. Okay, and since the oil is splashed, it fills the gaps, and it provides the lubrication, and because of gravity, again it will fall down, and again it will be picked up, and again it will be splashed. Okay, so this is the principle of splash type lubrication. And in some small compressors, small scoops or dippers are attached to the connecting rod, which picks the oil and throws it onto the rubbing surfaces. Okay, so small dippers or scoops are attached to the connecting rod. So whenever the connecting rod goes down into the oil sump, the scoop picks up some oil and throws the oil onto the rubbing components. Okay. And in small high speed compressors, flooded type splash lubrication is used. And in these modified type, slinger rings or screws are used for lifting the oil above crankshaft or main bearings, from where the oil floods over the rubbing surfaces. Okay, if you are using a splash type in high speed compressors, then a lot of oil may be thrown. Okay, so this may create oil carryover problems. Okay, so in such cases, they use normally a helical screw which will carry the oil. Okay, so the oil carryover is reduced. So this prevents excessive oil carryover. Okay, if the refrigerants are not soluble in lubricating oil, then there is a possibility of oil being carried away from the compressor and deposited elsewhere in the system. This is another important problem. If the refrigerant is not soluble, then oil will be carried out. Okay, out of the compressor. So in such cases, we have to use what is known as the oil separator on the discharge side of the compressor. Okay, from where the oil is separated and sent back to the compressor. So let me quickly conclude what we have discussed in this lesson. In this lecture, the following topics were discussed: selection of principal dimensions of reciprocating compressors, methods of controlling the compressor capacity, lubricants and methods of lubrication. Okay, and in the next lecture I will discuss other types of positive displacement type of compressors. Thank you.